How do modern cloud-native systems automatically recover when containers crash? And how do Kubernetes engineers manage massive distributed infrastructure without manually controlling every server? The answer lies in one of the most important technologies in modern backend engineering and cloud infrastructure, Kubernetes. And in this series of explainers, we're going to break down Kubernetes concepts one by one in a way that is visual, intuitive, and deeply practical. Whether it's pods, replica sets, deployments, services, namespaces, networking, scaling, or troubleshooting, this series will help you not only understand Kubernetes for real-world development and production systems, but also help you crack the CKAD exam with confidence. And if you're preparing for DevOps roles, cloud engineering interviews, platform engineering, or back-end system design interviews at companies like Google, Amazon, Microsoft, or Uber, these concepts are absolutely essential. But don't worry, we're not learning Kubernetes through boring documentation and static slides. In this explainer, we'll use anime-inspired storytelling, cinematic dark mode visuals, and real-world production engineering scenarios to make Kubernetes concepts feel incredibly intuitive. You'll see how Kubernetes behaves like an intelligent battlefield commander, how containers self-heal automatically, how traffic routes dynamically across distributed systems, and how modern cloud infrastructure stays resilient even under massive production load. By the end of this explainer, you'll not only understand Kubernetes core concepts deeply, you'll start thinking like a cloud-native systems engineer.
All right, here is our mission for today. We're going to build straight from the base unit, pods, and then scale up to replica sets, deployments, namespaces, services, and finally we'll arm you with your CKAD imperative command arsenal. Let's move.
Section 1. The base unit, pods, the foundational building block of the cluster.
So, in Kubernetes, the pod is literally your base infantry. It's the smallest, most fundamental deployable unit in the entire ecosystem. It physically runs your containers. But here is an absolutely crucial architectural rule you gotta remember. When we need to scale up to handle more traffic, we scale by adding more pods, never by stuffing more containers into a single pod. Think of it like deploying more mechas to the battlefield, right? You don't make one mecha unnecessarily complicated. And for those of you taking the CKAD exam, write this down right now. Kubectl Describe Pod is your ultimate diagnostic tool. If your pod is failing, always check the events section at the bottom of that output. It's basically like reading the unit's black box telemetry.
Now let's talk about how we actually deploy these units. You basically have two approaches. The blueprint is your declarative YAML. That's a precise desired state mapped out long before deployment. Then you have the imperative quickcast. That's your kubectl run command, perfect for deploying instantly on the fly. But you got to pay close attention to the live editing rules here. While you can edit a few things live, like the container image, there's a strict catch. Most spec fields are completely immutable, meaning you cannot change them mid-battle. No way. To alter them, you actually have to extract the YAML, delete the pod entirely, make your edits, and recreate it from scratch. That's just a fundamental law of Kubernetes physics.
Moving on to Section 2. High availability with replica sets, or as I like to call it, the self-healing cloning matrix.
Okay, so the crucial problem we run into here is that single pods on their own are incredibly vulnerable. I mean, if a physical server node goes down, that pod is just destroyed. Enter Level 2, the replica set. Think of this as a cloning matrix running constant, non-stop state checks. A replica set's entire purpose in life is to ensure that a highly specific number of pod replicas are running at any given exact millisecond. It's constantly comparing the desired state you requested against the actual current state of the cluster. If a pod crashes in production, boom, the replica set instantly spins up a new clone to replace it. It is literally the absolute core engine of Kubernetes self-healing and high availability.
Let's look at the YAML blueprints and see how this actually builds out. In our blueprint, say we're declaring we want exactly 3 replicas. There is an absolute CKAD exam critical trap you need to watch out for here. Selector.match labels. It is strictly required, and the label you define there must perfectly match the labels defined down in your pod template. If they don't match, the cloning matrix basically goes blind. It won't recognize or adopt those pods, period. You also have an imperative command arsenal at your disposal to instantly scale those replicas up to, say, 6, either by targeting the name directly or just using the YAML file.
But listen to me carefully on this next point, because this is critical for real-world production engineering. If you delete a replica set, you instantly destroy all the pods managed by it. It cascades destructively. Seriously, do not drop that command in a live environment unless you are fully, 100% prepared for that infrastructure wipe.
Section 3. Deployments, the tactical commander. Zero downtime rolling updates.
All right, let's elevate our strategy a bit.
We've gone from basic vulnerable pods to self-healing replica sets, and now we hit level 3, deployments. Deployments act as the ultimate tactical commanders sitting right above those replica sets. Now, why do we need this third layer? Well, because in the real world, you have to update your applications without dropping live user connections. Deployments orchestrate zero downtime rolling updates. They gracefully spin down the old replica set while simultaneously spinning up a new one. And here is a golden exam rule for you. Always prefer a deployment over a bare replica set. Deployments give you the power of instant rollbacks, which, trust me, is a massive CKAD topic.
So what does the control console for our tactical commander look like? Well, the YAML blueprint looks very similar to a replica set, but the kind field is now deployment. And kubectl create deployment is your absolute fastest way to spin up infrastructure imperatively during a high-stakes exam. But the real magic happens when you control the exact flow of an application rollout. Let's walk through the exact tactical steps for managing a deployment lifecycle during a super high-stakes production upgrade. Step 1. You trigger a live update using kubectl setImage to push a new container version. Step 2. You immediately monitor the battlefield with kubectl rollout status to watch the new pods gracefully come online. Step 3. If something feels off with the new code, you check the timeline with kubectl rollout history. And finally, Step 4. Your ultimate panic button, kubectl rollout undo. That single command instantly tells the infrastructure to revert your application completely back to the previous stable state. It is an absolute lifesaver.
Section 4. Namespaces. Virtual cluster territories. Isolating dimensions on a single hardware cluster.
So namespaces shift our perspective from executing workloads to isolating them securely. Namespaces are essentially virtual clusters backed by the exact same physical cluster hardware. This is exactly how you completely separate your dev, staging, and prod environments without needing entirely different physical servers. But there's a catch for cross-namespace communication. It requires a very specific DNS teleport coordinate format, and you absolutely must know this.
Let's drill down into that cross-namespace communication DNS string so it sticks in your memory permanently. It follows a very strict 4-part syntax: service name dot namespace name dot svc dot cluster.local. So, for example, if you have a database service named DB sitting in the staging namespace, other pods reach it via db.staging.svc.cluster.local. This is the precise teleport coordinate that bridges the dimensional gaps between your virtual territories.
Of course, isolated territories require strict rules. This is where resource quotas come in. This is how a tactical commander enforces resource limits per team. Say, capping a development namespace to a maximum of 10 pods and 4 CPUs. That prevents some rogue script from draining the entire physical cluster's resources. Also, a vital command for the exam is switching your active dimension. Using kubectl config set context allows you to change your default active namespace. This is a massive time saver because it saves you from having to type -namespace on every single command during the test.
Section 5. Services. Routing network gates. Ensuring reliable networking across distributed systems.
Okay, the crucial problem we have to address now is networking. Pods are ephemeral, right? They die, they get cloned. Their IP addresses are literally constantly changing. So how does traffic ever reliably reach them? That brings us to level 5, services. A service acts as a stable traffic shield and gate matrix. We have 3 main types to remember. First up, cluster IP. This is your default. It provides an internal virtual IP strictly for pod-to-pod backend communication. Second is node port, which opens a specific port across all your physical nodes. This is great for exposing a dev web app externally. And finally, load balancer, which integrates directly with your cloud provider for public internet production access. Now, wiring those gates together can be a little tricky, but mapping the ports makes it perfectly clear. Target port, that's the actual port on your pod where the application itself is listening. Port is the internal port of the service itself. This one is always required. And node port is the external port opened on the physical server. If you don't manually specify it, Kubernetes automatically assigns a high port between 30,000 and 32,767. And here's a massive exam tip. If you write a service spec and completely forget to define the type field, Kubernetes automatically defaults it to a cluster IP.
Section 6. The Exam Imperative Arsenal. Speed casting for CKAD's success.
All right, let's pivot to our final phase, pure tactical speed for crushing the CKAD exam. You simply cannot afford the time to write YAML from scratch in that test. Your ultimate time saver is the generator command, -dryrun = client o YAML. This is a real game changer. It casts out fully formed boilerplate YAML without actually deploying it, giving you a perfect template to modify instantly. You also want to master shortcuts to create and expose a pod simultaneously, instantly forge config maps and secrets directly from literals, and quick scale your deployments. Seriously, memorize these overdrive commands.
Finally, let's talk about API versions. Using the wrong API version is literally the #1 trap that fails candidates. You must memorize these classes. Core objects like pods, services, and namespaces use simply v1. The apps class, which includes our tactical commanders like ReplicaSets and deployments, uses apps/v1. But hey, if you ever freeze mid-battle and forget, use the command kubectl explain followed by the resource kind. It will print out the correct API version and all available fields directly in your terminal. It acts as your built-in tactical manual.
So that's the foundation of Kubernetes, the orchestration system powering modern cloud-native infrastructure. We explored how pods run workloads, how replica sets maintain high availability, how deployments safely manage updates, how namespaces isolate environments, and how services enable reliable networking across distributed systems. From scaling microservices and self-healing infrastructure to production deployments, cloud-native applications, and resilient distributed systems, these concepts form the backbone of modern DevOps and platform engineering. And once you truly understand Kubernetes core architecture, you begin to understand how companies operate infrastructure at internet scale. This is exactly the kind of engineering knowledge that separates someone who merely runs containers from someone who designs and manages production-grade distributed systems. If you enjoyed this explainer, make sure to like, subscribe, and share it with anyone learning Kubernetes, DevOps, cloud engineering, back-end systems, or distributed architecture. And in the next explainer, we'll break down another powerful cloud-native engineering concept used inside the world's biggest tech companies.